So in this lecture, we're continuing with kind of like a continuation of space groups, but here we'll be looking at what's called Miller Indices. So these are like the planes that make up crystals. And so when you collect a crystal structure, when you collect data, you're actually collecting the intensity of these different planes in the crystal. So these are planes that contain atoms, and then they diffract X-rays, and from that we can get the intensity of the planes. And as we'll see, certain crystal systems have certain sets of planes that are equivalent. That's why it doesn't take as much data to for those types of crystal systems, for example, cubic. So we'll go ahead and get started this morning. And so some of the earliest ways to describe the appearance of crystals was by looking at the faces of the crystals. So the external components of the crystals that gave it shape. And what they consider forms were groups of related faces. So this is similar to what we'll be doing with Miller Indices. So we have certain sets of what we call planes, and there are certain groups of planes that are related to one another, be it from symmetry, whatnot. So when we're describing the atoms and crystals, we're making reference to the directions used to describe the overall structure. So we're talking about directions, which are referring to the crystallographic axes. Again, this is A, B, and C. Give me 1 second. And then the planes are like the grading that allows us to do X-ray diffraction. So planes are going to be along the different types of crystallographic axes. So for example, the 100, as we see, is along the A axis, because the 1 refers to the A axis, the other two the B and C axis. And so by knowing the types of planes of the crystal, we can get many different types of properties, such as the optical behavior, electrical conductivity, etc. And so we're going to be talking about two different things. So we're going to be talking about the direction, which is a vector, and we're going to be talking about a plane. So when we have a vector, we can actually use that to determine planes as well. So vectors and planes are two different entities, but we can go back and forth between them. So we're mainly interested, at least in this lecture, the planes. And so when we're talking about the directions, we're talking about them as vectors, and we use the coordinates u, v, and w. And so the vector usually points from the origin to another point in the unit cell, or it can go beyond a unit cell. Now, when we're talking about vectors, and this is important, we use them in brackets. So when you see these 3 numbers in brackets, it's referring to a vector. Again, this is the u, v, w coordinates of a vector. And for negative values, they usually symbolize them with a bar on top of the number. And so vectors, again, are denoted by the brackets. And that's important because when we talk about planes, they're actually denoted by a different symbol. So these are all examples of vectors. So the way you determine the vector coordinates is you draw the vector and you just subtract the starting coordinates from the final coordinates. Now, if this is the origin, if your starting coordinates are the origin, then the vector would just be the final coordinates. So for example, if we drew a so if this is our origin here, so that's 0, 0, 0, and then from that we drew a vector in this direction which had the coordinates 0, 1, 1. So then this would be the direction 0, 1, 1, because we started from the origin. So if you start from the origin, the coordinates for the vector is very easy. It's just going to be wherever your, or the direction of the vector is going to be very easy. It's just where your final coordinates are. Now, if you have a fraction, we're going to have to multiply by the smallest multiplier to get rid of the fraction, because you cannot have fractions in directions or in planes. They have to be integer-based numbers. And so some crystallographic directions can be assigned by inspection. So just by looking at the direction, you can determine what the direction would be. So for example, if we have, if this is our origin here, and let's say we want to draw a vector out to this point. I know it's not a straight line, but it's freehand. So this is the coordinate, for example, 1, 1, 1. And so our vector, since we started at the origin, this would be the vector, or not, excuse me, yeah, the vector, the direction of the vector is 1, 1, 1. Now, if we decided to, another example, and again, it's always good to start at the origin if you can, because that makes everything easier. Let's see. So if we drew a vector like this, you know that this is A, this is B, so what we're doing is we're going in the negative B direction. So let's say this is a unit cell, another unit cell here. And so this coordinate here would be 1, negative 1, 0, because we went backwards on the B axis, which is y. And so the direction of this vector would be 1, 1 bar, 0. Because the C8, we did, on the C axis, we didn't move anywhere, so it's 0 direction. So this is the 1, negative 1, 0 direction shown here. And so just like with atomic positions, crystallographic directions can be described by fractional coordinates. And so the vector points to a point in the unit cell. And so here if we have, so if this is the origin, we can actually have it extend through multiple unit cells. So here we have, we've gone 2 unit cells over on the y-axis. So that's the coordinate, that's where the 2 comes from. We've gone up 1 along the A and up 1 along the C. Now, the reason we went to 2 unit cells is because if we look here at this point, let me get it. Here we would have, for example, if we stopped at that point, it would be the direction 1, or excuse me, the coordinate it would be, what is that? 1, 1. Oh, never mind. Yeah, don't worry about that. So just to let you know, for vectors, you can cross multiple unit cells to get a direction. So this is the 1, 2, 1 direction. And to show that when you're not starting from the origin, even though it's the same direction, they're going to be parallel to one another. So here, if we look at this, for example, this is the 0, -1 direction starting at the origin, and this is the 0, -1 direction starting off the origin. So you see that these are both parallel to one another. So even if you have different origins, the same direction is going to be parallel when you shift it off the origin. So here we've shifted it off the origin, and you can see that they're both parallel. Same goes for the -1, 0, -1 direction. And so we denote families of crystallographic directions as, in the brackets, UVW. So whenever you see the bracket, or excuse me, these greater than, less than signs, this denotes a family of crystallographic directions, meaning that they're all related through symmetry. So to give you an example of this, let's say we have tetragonal crystal system. And here you know A equals B, not equal to C. This is just to give you a little example of what we mean by family of directions when everything in it is equivalent to the symmetry. So for example, if we had the directions 1, 0, 0, 0, 1, 0, -1, 0, 0, and 0, 0, -1. So in tetragonal system, all of these directions are equivalent because the A equals, oh snap, I made a mistake. Not this one. It should be the 0, 1, 0. So these directions are, so this is the 1, 0, 0, 0, 1, 0, -1, 0, 0, and 0, -1, 0. And these directions are equivalent because in the tetragonal system, A equals B. So you would denote these as a family with something like this. So you could say that these are all equivalent for the 1, 0 direction. So this could be the 1, 0, 0 family, which includes all of these directions because they're all equivalent because A equals B. Now for C, C would have its own family. So if we looked at C, because the C axis you know, we would have for the 0, 0, 0, 1 direction, this would include the family, for example, 0, 0, 1 and 0, 0, negative 1. Oh, not the negative, keep it negative. And so this would be its own family. So the 1, 0, 0 family will include these directions in tetragonal, and may a few others that I didn't mention, but these 4 main ones, because again the A and B are symmetrical, or are the same. Since the A and B axis are the same, those corresponding directions will be equivalent. So all of these directions will be included in the 1, 0, 0 family. Now for the C axis, which is not equal to A and B, it has its own family. So for the 0, 0, 1 family, it would include the 0, 0, 1 direction and the 0, 0, negative 1 direction. Likewise, for the family, just to show you one more example of a family, if we had the 1, 1, 0 family, this would include the 1, 1, 0 and the 0, 1, 1, and of course the, not the 0, 1, 1, my bad, 1, 1, 0, no, no, A and B, yeah, negative 1, negative 1, 0 family. So again, these can contain equivalent directions. That's what we mean by family. Includes both the positive and the negative directions. And this is based on the constraints of the crystal system. So for a cubic, which has, remember for cubic A equals B equals C, so the 1, 1, 0 is equal to the 1, 0, 0, the 1, 0, 1 and the 0, 1, 1 direction. So all of these would be the 1, 1, 0 family, because they're all equivalent because A equals B equals C. So all of these directions are going to be equivalent to one another. Now as for tetragonal, where we have A equals B, but B doesn't equal C, the 1, 0, 1 equals the 0, 1, 1, because again, A and B are the same, which is equal to the 1, 0, 1 family. But 1, 1, 0 doesn't equal 1, 0, 1 or 0, 1, 1 because A and B are not the same as A and C and B and C. Because since A and B are the same, when they're with C, they're equivalent positions. So the 1, 0, 1 family would include these and their corresponding negative directions. But it's not equal to the 1, 1, 0 because A equals B doesn't equal C. So that is not an equivalent direction. There you go. And so here the 0, 1, 0, 0, negative 1, 0 would be, in this case, the 0, 1, 0 family. And then this is an orthorhombic crystal. So A doesn't equal B, doesn't equal C. No, is this tetragonal? I don't know. Maybe it's tetragonal. But the 0, 1, 1 and the 0, negative 1, negative 1 is the 011 family. Oh yeah, this is orthorhombic. Because again, you have less restrictions, you're going to have less equivalent directions. And this is important because the more equivalent directions, aka planes, you have, the less data you need to collect to get a whole sphere of data, a whole set of data for that particular crystal, because they're all equivalent directions. So you can use symmetry to generate the rest of the data. So those were talking about directions. It wasn't until the 19th century we had a mineralogist, William H. Miller, that developed a scheme for distinguishing the faces of crystals and measuring their angles. And so this can be corresponded to the real crystal faces, planes of atoms. But again, the plane itself is only a reference that we use for crystallography. So the planes that have on the external faces of crystals can also be used to describe what's inside the crystals. And that's where we get what's called the HKL planes, or what's on the inside of the crystals that diffract the X-rays. So each plane consists of a series of atoms on it. So when the X-rays strike, it diffracts the crystal, diffracts the X-rays. And so planes are better used to describe intercepts along axes, just like we use directions. So we just talked about how directions are used to determine on any unit cell. We can also use planes as well, and where they intercept on certain axes, we can use as a reference. So for example, if it only intersects the x-axis, it's a particular plane. If it only intersects the y-axis, it's a particular plane as well. So what we call these are called Miller indices of crystal planes, referred to as the HKL values. And just to give you a little prequel of what's to come, based on which HKL values are present or absent in a crystal data set, you can actually determine the centering and symmetry of a crystal. And so that's what the computer does. It looks through all these different types of HKL planes, see which ones are absent, which ones are present, and from that you can determine what the symmetry is of that crystal and what the centering of that crystal is. Well, that's actually something we're going to talk about next week as well. So that's where we're going to be utilizing these HKL planes. And so the plane is actually an inverse of the intercepts along lattice vectors. And so the way we describe a crystallographic plane is we use parentheses. Remember, for vectors, it was brackets, but for planes, we use parentheses to indicate the H, K, and L value. So H refers to the A-axis, K refers to the B-axis, and L refers to the C-axis. Just like we had with the vector, U was along the A, V was along the B, and W was along the C. Most of the time, these are perpendicular to one another, but not always. And so the way we determine the HKL plane is, first off, if the plane crosses the origin, we need to either select an equivalent plane or move the plane off the origin. So if your plane crosses the origin, the first thing you got to do is kind of shift it away from the origin so you can see which axes it crosses and which ones it doesn't. So for example, in this plane here that we have at the bottom of the screen, you'll notice it's not on the origin, so we don't have to shift it. But what you also notice is that it will never, remember, planes are two-dimensional. This will never cross the z-axis. So since it never crosses the z-axis, it has a z-intercept at infinity. So anytime your plane doesn't cross an axis, it's given the value infinity as the intercept. The next thing you need to do after you've determined it's not on the origin is determine where where does it intersect on the A, B, and C axis. So for the z, we knew it was infinity because it never crosses the z-axis. For A, it's like 1/2, or for X, it's 1/2 the A axis. So we would say 1/2 for A, and for Y, it crosses at 1. So these are the coordinates of this plane. So again, it doesn't ever cross the z-axis. The z-axis will never cross because as you shift it off the origin, the plane never intersects the z-axis. So we give it the coordinate infinity. The plane crosses the x-axis at 1/2, at a half of the a-axis, so 1/2 the value, and the plane crosses the y-axis at 1. So then what you do is you take the reciprocal of this, of these fractional intercepts. So we get 1 divided by 1/2, one over 1, and 1 over infinity. And so this becomes 2, 1, 0. Now, if there's any negative values, you would denote it by a bar. So you would drop the negative sign and put a bar on top of it. And then if there's any fractions, you have to multiply by a common multiple to get rid of the fractions. And then finally, you close it with parentheses. So this is what we refer to as the 210 HKL plane. And this is how you derive the value of the HKL plane. And so what you get once you complete a full data set is you get a HKL file that contains all the relevant HKL planes and their intensities of each plane. And from that, you can determine what the symmetry of your crystal is and also the centering, so you can identify the crystal system and the space group. Because certain planes, based on symmetry, as we'll learn next week, are what we call systematically absent. So those reflections won't show up. For example, if you have a screw axis, there are certain reflections that will be absent. For a glide plane, there are certain planes that will be absent. So when we talk about a reflection plane, we're talking about the HKL plane. And so by knowing which one of these planes are absent can give you information about the symmetry and also centering. So here we have some examples. We have a unit cell, and we have 3 planes. And so we're going to look at each one of these and determine the fractional, the reciprocal intercepts, and then the Miller indices. The only difference from going from reciprocal to Miller indices is making sure you don't have any fractions and the negative sign is replaced with a bar. So if we look at A, and so down here is the origin of this unit cell. It's right here. So A intercepts the z-axis at 1, intercepts the x-axis at 1, and the y-axis at 1. So again, it crosses. So first off, it doesn't touch the origin, which is good. Secondly, it crosses the z-axis at, you could say, 001 coordinate. It crosses the x-axis at 100 coordinate, and it touches the y-axis at 100 coordinate. So by knowing these 3 coordinates, we can get the fractional intercepts. For A is 1, 1, 1. So it crosses the x, y, and z at the coordinate 1. And so the way we know it's 1 is because this is 1 unit cell shown. And so here, since it crosses at the corner of the y or the b axis, it's 0, 1, 0 coordinate. So these are our fractional intercepts where the plane crosses the x, y, and z axis. Then we take the reciprocal. Since they're all 1, it's just going to be the same. And since none of them are negative, there's no fractions, this would be the 1, 1, 1 HKL plane. So it looks like a triangle. Next we go to plane B, and let me highlight plane B so it makes it easier to see. So B is right here. In red. So you'll notice first off, it doesn't cross the origin, which is good, so there's no shifting involved. Secondly, it crosses the x-axis at 1, the y-axis at 2, and it never crosses the z-axis. So that would be infinity. Since it never crosses, it's given the coordinate infinity. So no matter how far you go in two directions with this plane, it will never cross the z-axis. So the fractional coordinates for B is 1, 2, infinity. Again, it's infinity because it never crosses the z-axis. Next, we take the reciprocal of these. We get 1, 1/2, 0. So notice here that this is a half, so we have to multiply something by all of these intercepts to get whole numbers. So we multiply by 2, we get the Miller indices 2, 1, 0. Again, the 0 is because this plane will never cross the x-axis. Excuse me, z-axis. So that was plane B. Now we'll look at plane C. Now plane C is kind of hard to see. That kind of rhymes. Plane C is kind of hard to see. But it's right here located. Right here. And so you notice that this plane crosses the origin. So that's not good. So what we want to do is we want to translate it 1 unit over and see what axes does it cross. So again, the reason we're translating it is because it crosses the origin. So we're going to move it 1 unit in the positive direction to see what axes does it cross. And when you move it 1 unit in the positive direction, you see that it only crosses the y-axis. It will never cross the x and z axes. It only crosses the y. And so from that, we get the fractional intercepts of infinity, 1, and infinity. Again, we shifted off the origin 1 unit. We notice that it only crosses the y-axis. So if we shifted 1 unit off the origin, it would be right here. And you see the only axes it would cross would be the y-axis. It would not cross the z or x-axis. So these are our fractional coordinates. We can convert them to reciprocal. And so 1 over infinity gives us 0. And since they're all positive, or excuse me, they're all integers, there's no negative ones, we can just write it as the Miller indices. So that's the 0, 1, 0 plane. So now, how could an equivalent plane to B also be drawn on the same diagram above? So B, remember, was the 2, 1, 0 plane. We can also draw an equivalent plane if we have these following set of fractional intercepts. So if we have the fractional intercepts 1/2, 1, infinity, you see we would also generate the same reflection plane. So we would get 2, no comma, sorry, 2, 1, 0. So the 1/2, 1, infinity fractional intercepts, not coordinates, intercepts, is the same as the fractional intercepts 1, 2, infinity. So those are equivalent. So whether you do the fractional intercept 1/2, 1, infinity, or the fractional intercept 1, 2, infinity, it's going to give you the same reflection plane. Look at a few more examples. So what's the difference between positive and their negative equivalent planes? So from the previous slide, we saw that plane C was 0, 1, 0 plane. Now if we move it to the left instead of the right, negative 1 unit over, it becomes a 0, negative 1, 0 plane. And so this is arbitrary whether you move it to the left or to the right, because what happens is you get a series of planes, and these are equivalent planes. So the 0, 1, 0 and the 0, negative 1, 0 are equivalent planes because their only difference is one was shifted to the right 1 unit, one was shifted to the left 1 unit. And so what happens is you get a series of planes that are equivalent, and that's how your diffraction gradient works for X-rays. So the X-rays come through. For example, the X-rays come in, they strike all of these 0, 1, 0 planes. So these are all X-ray photons striking the plane in the same position. And then they all diffract the same, and this ends up as a diffraction spot on the detector. So that's how this works. So the X-rays strike the planes, and since they're all equivalent, it's going to strike it all at the same place. Then it's going to diffract. That's going to form your reflection intensity. So just a few more examples. So if we look at the top one here, you see that we have this plane right here. What you notice is that it crosses the origin right here. And so since it crosses the origin right here, we have to shift it. And so we're going to shift it up 1 unit. So I'm going to shift it up 1 unit. Oh, excuse me. No, it doesn't cross the origin because the origin is right here. So this is the X. This is the Y. So what's happened is it shifted it. This is confusing. Let's see. Well, let's change the origin because. All right. So we'll move the origin to make it for illustration purposes. We'll move the origin here. So this one sits on the origin. So if we move it up 1 unit, it becomes right here. And so you notice from this that the plane only crosses the z-axis. So again, we should move the origin to down here. So we have the x, y, and z axes. If we shift it up one, you see it only crosses the z-axis. So since it only crosses the z-axis, that means the h and k, or the x and y, are 0, the z is 1. And so this becomes the 0, 0, 1 reflection plane. Because again, it only crosses the z-axis once we shifted it up. Now we come to the next one. So here the origin is right here. And so you'll notice that we've dropped down 1 unit and we went over 1 unit. Now this is on the origin, or since it crosses the x-axis here, if we move it off, if we shift this plane, you would see that it would never cross the x-axis. So if we moved it to the left or move it to the right, this plane here would never cross the x-axis if we move it off the origin axis. So again, we dropped it down 1 unit in the z direction, and we moved it 1 unit in the y direction. Again, if we just move this slightly off the axes, since it's right on the x-axis, if we move it slightly off the axes, you see that it would never touch that axis. It would never touch the x-axis. And so therefore, this would be the 0. Oh, it should be, that's wrong. It should be 0, 1, negative 1. Because we moved down 1 on the z, and we moved to the right on the y. So this is the 0, 1, negative 1 reflection plane. Because again, we moved down on the z 1 unit, we moved to the right on y. Again, x is 0 because if we shift this just a little bit off the axis, you see that it would never cross the x-axis. Likewise, if we look at the next one, here we have the origin is behind the plane. So you see that it crosses the x-axis at a half and the z-axis at 1. But you'll notice it will never cross the y-axis because the y-axis is actually behind this plane. So then the HKL indices would be 2, 0, 1. Because again, it crosses the x-axis at a half, it crosses the z-axis at 1, and it will never cross the y-axis. So this is the 2, 0, 1 reflection plane. And then lastly, we look at the fourth example. So here it crosses the x, and again, the origin is behind the plane, so this plane does not cross the origin, so we don't have to shift it. But here it crosses the x-axis at 1/2. It crosses the y-axis intercept at 1, and it crosses the z-axis at 1/2. So these are the fractional intercepts. And so we get the HKL value of 2, 1, 2. Now going back to the first example, if we go back to the original set of the original origin, and we draw it consistent with the others, we can say, you know, this is the X, Y axis. It's a little bit confusing because the origin is up here. Usually at the origin is where you have the XY axis. So they shifted this plane down 1 unit on the Z axis. So if you take this plane and kind of move it a little bit up or a little bit down, you would notice that it would never cross the X or Y axis. So again, if we move it a little bit up or a little bit down from where it is, it would never cross the X and Y axis. So therefore, if we represent this as the origin, then this would become the 0, 0, -1 reflection plane. So remember, if the origin was here and we shifted it up, it would be the 1, 0, 0, 0, 1. But if we put the origin here and shift it down, it becomes a 0, 0, -1. Just a common, or just a kind of a characteristic that makes it easy to identify the 1, 0, 0, or a neat trick, I should say. So if you want to know the 1, 0, 0 plane, it's going to be, the plane is going to be in the ZY plane. Because if you move it off the ZY plane or ZY axis. So if you see a plane that is in the ZY axis, ZY plane, so for example, ZY plane is right here. If you see a plane in the ZY plane, that's going to be your 1, 0, 0 plane. Because if you shift it off the origin 1 unit, it's never going to cross the Z or Y axis. Likewise, an easy way to remember the 0, 1, 0 plane is that it's going to be in the XZ plane. So now if we look here, if we're in the X, and this is understood that the origin is down here, for example. Let me keep the origin up there. So now the XZ plane is right here. And so if we shift the XZ plane 1 unit to the right, you see it would never cross the XZ axis. So that's how you know it's a 0, 1, 0 reflection plane. And then lastly, if you have the 0, 0, 1 reflection plane, it's going to be on the XY plane. Because when you shift it off the origin, it's no longer going to cross the X or Y axis. So this is a little neat way to help you remember at least the main reflection planes, what they look like. So here, this plane shown in the first example is on the XY plane. If, for example, this is the origin, so then if we move it up 1, it becomes a 0, 0, 1 H-scale plane. So just like with directions, we do have equivalent planes that can be placed into families, and these are generally denoted with the brackets. So if you see a bracket with HKL values, this usually encompasses a family of equivalent reflections. And the As with directions, it's dependent on the crystal symmetry, because the crystal symmetry will show you which planes are equivalent and can be included in the HKL family. Now for cubic, which has the most constrictions in lattice parameters and the highest symmetry, all combinations of given HKL, as well as those with positive and negative values, are included in the HKL family. Because for cubic, all of the links are the same. So for example, the 001, 010, and 100 would all be equivalent reflections. So now I got a few examples I wanted to show you in a second. Yeah. So here's showing you, for example, family members of the cubic lattice. So what are family members? They should be brackets, not less than. That's for directions. But here, oh yeah, bracket. Just note that these should be brackets. And so for the 100 family, it includes all of these reflections. Because again, the reason this is because the A, B, and C axes are all the same. So whether you have the 100, the 010, or 001, and their negative counterparts, they're going to be equivalent. Likewise, the 110 family would contain all of these identical reflections. And notice that the 110 family also contains, for example, the 011 reflection as well, because for cubic, the A, B, and C axes are all the same, so therefore they're all equivalent. Likewise, for the 111 family, all of these are equivalent reflections. And so for a cubic crystal system, there's not a whole lot of data you need in order to generate all the symmetry equivalent reflection planes. And so the reason these planes are important is because now we can calculate something called the D spacing. So the distance between the different atomic reflection planes in the crystal. And this is important because if you remember from Bragg's law states n lambda, n lambda equals 2d sine theta. So we have n lambda, let me draw lambda here. N lambda equals 2d sine theta. Now this d is the d spacing between the corresponding HKL plane. So the way we calculate the d spacing is dependent on the type of HKL plane it is. So for example here, if we want to know the d spacing for the 100 plane, this is going to be equal to the a-axis because the a-axis is the 100 plane. Now if you wanted to know what the 200 plane d spacing was, well, it's going to be half the a-axis, because if the a-axis is the 100 plane, the 200 plane would be 1/2 the a-axis. So for example, if the a-axis equals 12 angstroms, or 12 angstroms, this would equal the d spacing for the 100. But for the 200, it would equal 6 angstroms. So the d spacing for the 200 would be 6 angstroms. The D spacing for the 300 would be 4 angstroms, and so forth. So by knowing and this can go both ways, so by knowing the D spacing, you can determine the unit cell axis lengths, or if you know the unit cell axis lengths, you can calculate the D spacing for the different equivalent reflection planes. And this would be the same whether or not if you had the 100, the 010, or the 001 reflection planes. So if it was a 010, that's the B axis. So if you know the value of the B axis, you can calculate the D spacing for the 100. Likewise, if you know the D spacing, you can calculate the B axis. So you can kind of see how now, when they collect reflection data, they can use that to determine the unit cell values. And also, if they know the unit cell values, they can calculate the D spacing for the different reflection planes. And so here's how you can take the D spacing and determine the actual relevant HKL values. And this is pretty cool here, because if you know the D spacing and you know the unit cell values, you can actually from that calculate the HKL value of that plane. And so for cubic, it's a very simple equation because A, B, and C are equal. So it's just the h squared plus k squared plus L squared divided by A squared equals 1 over D squared. So again, if you know the D squared and you know the A value, you can calculate the HKL value, HKL plane for that particular D spacing. Now, as you go to lower symmetry, you see that the equations become a little bit more complex, and that's because there's less restrictions or constraints on the lattice parameters. So again, you don't have to memorize these equations, you just have to know how to utilize these equations. And just to show you triclinic, and don't worry, triclinic, the computer does it, because as you can see, it's a very messy calculation because there's no restraints in the lattice parameters, so it's a very involved calculation to determine for example, the HKL values for a particular D spacing. But again, these equations show you how you can take the D spacing and the unit cell value and find the HKL plane, or if you know the HKL plane and the A value, you can calculate the D spacing and vice versa. So this is how you get between all the different units or parameters, I guess you said. And so this is important when we look at D spacing on X-ray diffraction. So as I said earlier, n lambda equals 2D sine theta. And as we learned very early on in the course, n is always set to 1. Lambda is either 1 or 2 numbers. If we use molybdenum radiation, lambda is like 0.71 approximately. And if we use copper radiation, lambda is approximately 1.54 angstroms. So both of these are in angstroms. So there's really not much you can do on the n and the lambda. Those are set for you. So the D is approximately or equal to lambda over 2 sine theta. So 2 theta kind of approximates the D spacing. It's proportional to the D spacing. And what you have to remember here is that the theta angle is inversely related to the D spacing. So lower theta, you get larger d spacing. At higher theta, you get smaller d spacing. So if you know the two theta values and you know your lambda, you can calculate the d spacing. And this is what's commonly done when we use X-ray powder diffraction. We can calculate the d spacing, and then once we know the d spacing, we can calculate lattice parameters. So once you know the lattice parameters, then you can calculate any HKL index for a peak in a powder pattern. And typically you can do this by inspection of calculations. And we're going to look at hopefully some examples of that. So this is pretty cool. So what you do is you do an X-ray powder diffraction pattern, which we'll show you in a little bit. You get the two theta values. You can calculate the d spacing. Once you know the d spacing, you can determine the lattice parameters. Once you have the lattice parameters, you can then determine the HKL values that are present for a particular diffraction pattern. So this is what a powder diffraction pattern looks like. So this is what we call one-dimensional data. X-ray, single crystal X-ray data is called three-dimensional data. So one-dimensional data just shows you the intensity versus the two theta, and that's the same two theta as what you see in the Bragg's law. So here we have a silicon crystal. It's in a cubic space group. It has the lattice parameter of 5.4307. Identify the HKL indices of the diffraction peaks observed at 2 theta of 69.1 and 76.45. So just by looking at this, we see here that this is the 69.10. This is the 76.45. So before we begin, I'm going to go back and write down the equation for the cubic system because I forgot it. So now we're going to do some math. You might want to put on your math cap. So let me backtrack a little bit. Here we go. So 1 over d squared. So I'm going to be, since it's cubic, I'm going to be using the first equation to determine the HKL values. So we have this diffraction pattern. It tells us the 2 theta is 69.10. Remember that we just saw on the previous slide that D equals lambda divided by 2 sine theta. So that's how we find the D spacing. So the lambda wasn't given, but this is done in the copper. So the lambda is 1.54. We know what 2 theta is. 2 theta is 69.10. So let me write this stuff for you. So again, we want to determine what the HKL values are for the unknown 2 theta positions, for the 2 theta positions. So lambda is roughly 1.54. 2 theta, 69.10. Let me draw the theta. Now we want theta because to use the equation, we got to have theta. So theta is half of 2 theta. So theta equals, do that real quick, 69.10 divided by 2. And this is something you need to remember because in powder diffraction or any type of diffraction, it's always given in 2 theta. But for the equation, which is D equals lambda divided by 2 sine theta, it's in theta. So always make sure you convert the 2 theta into theta. That's lambda. So this is the equation we're going to use to calculate the d spacing. So let's go ahead and do that. So d equals 1.54 divided by 2 times sine 34.55. All right. D equals 1.54 divided by sine of 34.55 times 2, get point. And then we get a d spacing of 102.4. Let me double check that because that doesn't, I was using my cell phone as a calculator. Oh, here we go. All right, that doesn't jive. Sine of 34.55 times 2. Oh, no duh, that's wrong. You should use a cell phone for a calculator. I get 1.13. I just had it. 1.1343. And I get a d spacing of about 1.3578. Okay, so that's the d spacing when theta is 34.55. Now that we know the d spacing and we know the value of a, which is given to us, and again, d spacing is calculated in angstroms because the wavelength is in angstroms. So now we know that we're going to use the equation 1 divided by d squared equals h squared plus k squared plus l squared divided by a squared. So that'd be 1 divided by 1.3578 squared equals, let me copy and paste. There we go, divided by 5.4307 squared. So again, we're doing all this to determine what the HKL index is for this 2 theta position. So we get 0.54241 equals divided by 2.949. Yep. So now move stuff around. So we get here pretty much it's 16 because it's 15.99. So 16 equals this. So we got to ask ourselves what values of h squared plus k squared plus l squared would add up to 16. So one possible solution, one possible HKL, and there could be several possible HKL values. So one could be the 400 reflection plane, because remember 4 squared is 16. That would give us that HKL. But then this is also equivalent to the 040 reflection plane and the 004 reflection plane. That's about all we can do, because if this is, say, for example, the 232, that would be 4 plus 9 plus 4. So this is pretty much the only set of indices that can give you 16. Because if you do 222, it would be 4, 8, 12. So the theta, the 2 theta of 69.10 is this reflection plane, the 400, or they're all equivalent reflection planes. So that's what 69.10 is. Now let's do the 76.45. Let me put that up just for a moment so you can copy it down or whatnot. And again, this is how you use 2 theta data and the lattice parameter to determine the HKL indices. And that's what Mercury does. If you ever go on Mercury, they have a simulated powder diffraction pattern software that you can tell the crystal structure, and it'll go in and it'll give you a simulated powder pattern, and it'll assign the HKL values for it. And that's exactly how it does it. It's the way we did it right here. So let's look at the other one. Let me clear out a couple of things. I hate to, but I have to. Okay. So now let's look at the second one, 76.45. So that's our 2 theta value. Our theta value would be half that. So 38.23. Now we want to calculate what the D spacing is. So D equals 1.54 divided by 2 times sine of 38.23. So the D spacing is 1.244. Notice that since theta got bigger, our D spacing got smaller. So now we know the D spacing, so we can set up our equation to solve for the HKL indices. So we have 1 divided by 1.244 squared equals h squared plus k squared plus l squared, divided by 5.4307 squared. So this will make you appreciate the software that does it for you. So Let's work this out. 1.244 squared 0.646 equals 29. Oh snap. 29.49. I think on the last one I put 2.949, but actually my calculator had 29.49. So on the last example we did, it should have been 29.49, not 2.949. So that was my bad. But on the calculator I did it right, but on the display I wrote it wrong because for some reason the scientific notation didn't register in my brain. So now we get we get 19 equals so I got 19 equals h squared plus k squared plus L squared. Let me just double check. Yeah. So now we got to come up with a series of HKL indices that equal 19. So let's see. H is 3, that's 9. 9 and 9 is 18. So if H is 3, K is 3, L is 1, does that add up to 19? Let's see, 3 squared, that's not 18, 19. So this is probably either the 331, the 313, or the 133 reflection plane. So again, all of these are equivalent because it's cubic system. They all have the same A, B, and C axes. And so this is how you take lattice parameters, 2 theta data, and then from that you can determine the HKL indices. So you have to do it by visual inspection and see, okay, what set of indices can add up to that particular value. Now for the scope of this class, we're mainly going to do high symmetry systems, like for example, cubic, tetragonal, maybe an orthorhombic, but you're not going to do something like monoclinic or triclinic humongous equation. And so this is how Mercury and other programs take the structure, and from that they can simulate the powder diffraction pattern by going backwards. So they know the HKL indices, they know the A value, they can calculate the D spacing and then get the 2 theta value for a particular wavelength. And that's how software calculates those types of patterns. So that's all for today. We'll continue with Miller indices. We don't have too much left on Miller indices. So I'll go ahead and we'll end the lecture for today. If you have any questions, feel free to ask.